So hello, what's up guys, welcome to my channel. In this video I will discuss the direct stiffness method for frames. So you can see on this screen we will solve this problem and we will find out the stiffness matrix for this structure using Excel sheet which is right here. I have made it. So let's first discuss the problem. We have the given structure which is a frame. We have defined the coordinate system. So this is our x direction, this is our y, and this is our z direction. So we need to determine the stiffness matrix K for the frame, and we have the E value, which is modulus of elasticity, the moment of inertia I, and the area of each member is 20 inch square. Right? So this is the member number 1, which is represented by this square 1. So this is our member number 1 and this is the member number 2, right? So if we want to calculate the stiffness matrix, we will first calculate the stiffness of member 1 and member 2, and then we will add it, right? So here it is shown manually. You can follow this procedure to manually calculate the stiffness matrix, which will take a lot of time. But in this video I will give you a shortcut, an easier method to calculate the stiffness matrix. So let's calculate K1, which is a matrix, stiffness for member number 1. So here we can see this is the member number 1 and it is shown here, right? This is the member number 1 applied by this 20 kF load, and its whole length is 24 feet, right? So this one is the near end of this member. Let me write it down. So this one is the near end, this one is the far end, right? This is usually represented by this arrow. Okay, so this arrow represents the direction, this arrow represents the far end, and this tail represents the near end. So we will going from this direction. So this is the near end and this is the far end for this member number 1. Now the unknowns are defined here, as you can see, 1, 2, and then we have this 3. Right, so these corresponds to the unknowns in the direction of 1, 2, and 3, which is related to this coordinate system. We have also taken the origin here, so this will be our 0, 0. Right, this is the origin, and this will be equal to 24. Let me write it, typewriter. So this end is basically our 24, 0. These are the coordinates, right? So this is necessary to determine the coordinates. And for this end I will write it here. This is 24 and 16, right? So these are the XY coordinates of this system. Okay, so now we want to calculate the stiffness matrix for this member. The length is already given, which is here 24. We need to calculate lambda x and lambda y only. Lambda x is basically the x2 minus x1 divided by length, right? x2 minus x1 divided by length. So here we have x2 24, right? And here we have x1 is equal to 0. So 24 minus 0 divided by length, which is 24, is equal to 1, right? Now lambda y is equal to y2 minus y1 divided by 24. So it is the y coordinate at here minus the y coordinate here divided by the length of the member. You are getting me, right? So here we can see the y coordinate is 0, and here also the y coordinate is 0 because this is the origin. So lambda y is 0 minus 0 divided by 24. That's all. You have calculated now everything, lambda x and lambda y, and we have these material properties. So let's go to the Excel sheet here. So here you have to enter these data. So we have the area A is 20 inch square, so I have put it here 24. The modulus of elasticity is 29,000 ksi, as you can see here. Then the moment of inertia is 700 inch 4. As you can see here, we have entered the moment of inertia. Now this is the length. So length is equal to 24 feet. So we have 24 times 12, 24 feet. So we have converted into inches. So we will enter 288 here, 288. And then we have the lambda x, which is equal to 1, the lambda y, which is equal to 0, right? So we have entered all these things. You have just to plug in these information, and this matrix will automatically calculate the stiffness for that member. So imagine if you have a frame with a lot of members, so it will really save your time. Now the stiffness matrix is calculated, as here you can see we have the near end here. Let me delete it. We have the near end here. So the unknowns are 8, 9 and 5. 8 is in x direction, so this is nx. So nx is equal to 8, ny is equal to 9, and nz is equal to 5. This 5 is in the z direction, right? At the far end we have fx, sorry. So fx is 1, fy is 2, and fz is 3, right? So we have plug in here, fx is 1, fx is 2, and fz is 3. Now on this side you can also plug in these values, right? So you can write it down, this value. Now let's compare it with the calculated values. So right here you can see the manual calculations. We have this stiffness matrix K1, which is calculated using these equations, right? It will take a lot of time. Now let me compare it with this. So let me bring it here, and we have here okay, so let me zoom it a little bit. Okay, sorry. Here you can see 2013.89, 2013.89, then we have 0, 0, and minus 2013.89, we have minus 2013.89. You can see here. Okay, so you just need to enter these information, 29,000, and all of the other information was already inserted. So we have ny, we have 0, then 10.2. Here you can see 10.19. Here you can see 1468. Here you can see 1468, then 0, then minus 10, then 1468. Similarly nz, which is 0, then we have 1468, then we have 281,944. So you can see 281,944. Then we have 0, minus 1468, and then 149.7. And similarly these 1, 2 and 3. So you can see minus 2013, we have 00, 2013, and then 00. Then we have this 2, minus 10. You can compare it with yourself. You can pause the video and compare all the values. So all the values are similar. So it will really cut your time, save your time. You just need to enter this area, modulus of elasticity, inertia, and length, and these lambda x and lambda y. Now let's go to this member number 2 and quickly plug in the values. So we will get K2. So for this member number 2 we have this arrow. So for member number 2 this arrow represent that this is the near end. Now I will delete it. For this member number 2 we have this near end and this is the far end. So near end we have 1, 2 and 3. I will write it down, 1, 2 and 3, right? And on the far end we have at the far end we have 6, 7 and 4. So we have 6, 7 and 4. Similarly here 1, 2, 3 and then 6, 7 and 4, right? And for member number 2 all the properties remain the same. We need to calculate the lambda x and lambda y and just plug in the length, right? So for member number 2 we have the lambda x which is x2 minus x1, 24 minus 24 divided by 16 which is 0, and lambda y is 16 minus 0 divided by 16 which is equal to 1. So let's plug in the values. Lambda x is 0, this is 1, and the length is 16 feet. So 16 multiplied by these 12, so this is 192. Boom, you have calculated the stiffness matrix for member number 2. So this is the K2 which is manually calculated here. Oh, I think there is some problem with the document. So let me reopen it. So you can see even in less than a minute you can calculate the stiffness matrix. So yes, this was the K2. Let me show you. 1, 2, 3. You can see 1, 2, 3, and here 1, 2, 3. So let's see 1. This is 34.41. It is rounded here, right? So I can unround it. It is rounded up, so we can basically, now you will see exact comparison. So you can see here 34.4170, right? So you can see here 34 let me drag it down. We are comparing K2, right? So 0, then minus 3304.03, and you can see the rest of the value. You can pause the video and compare each value yourself. Okay. So this is really helpful. I can provide you this sheet, Excel sheet, so you can use it. It also have a direct stiffness method for trusses and beams, and simple beams also. So I hope you will like this video. You can then calculate the structure stiffness matrix by just adding these two values, K1 and K2. It's just the algebraic summation. It's easier and you can calculate it. Like you can see here, I will show you just one example. This is one typewriter. This is 1, 2, 3 and so on, and this is also, I will write it here, 1. So for calculating 1, this initial first value, we will add 1, which is here 1, this value. Sorry. So 1, which is equal to 34.41, right? This was 1 and 1 cross this term, right? 1. So this is 34.41 plus, let's go to the K1. Here we can see 1 and 1, so which is equal to 2013.89. So we will plus 2013.89. so here we have 2048.3. this is the 1 value. So this is the structure stiffness matrix, and here you can see the 1 value is 2048.31. so you can also calculate other values by the similar procedure. So I hope you will like this video, and if you like this video, give it a thumbs up, and also tell me that if you want this file, I will just put it in the description, just comment down, I will share it with you. So thanks for watching. Also subscribe my channel.